gracias y bueno, espero tenerte pronto en Argentina de nuevo.
Muchas gracias. Estoy ansiosa por volver y interactuar ahora, siempre que la pandemia lo permita.
Sí, ya lo vamos a hacer, vamos a interactuar. No te preocupes,
Muchas gracias.
un asado va a haber. Bueno,
Sí, gracias por la invitación. Chao.
well, thank you, Maria, for his presentation. We move to the next second speaker on these flash presentations. Also from Argentina, Rodo Acosta, de la Universidad Nacional de Córdoba, nos engalana la sesión flash. Rodo, well, I will say it in English. Rodo works at the Lanais NMR Institute, laboratory at the FAMAF in the National University of Córdoba in Argentina. He's a professor and also staff researcher from CONICET. He has a PhD in chemistry, in physics. Sorry, I almost insulted you. Sorry, physics from the UNC, and also is a group leader of a partner from the Max Planck Institute for Polymer Research in Mainz. He holds collaborations with Aachen, also Uni Ilmenau in Germany, and the City University of New York. And his interests are dynamics of confined fluids in porous media, hyperpolarization techniques in nuclear magnetic resonance, a collaboration with also national oil company YPF and the technological company, which is ETEC, in the characterization of non-conventional oil reservoir or shale with NMR-related techniques. So without further ado, I give you Rodolfo Acosta. Rodolfo, adelante. Gracias por participar.
Gracias, Matías. Do you see the presentation okay? Sound is okay?
Yeah, it's perfect. We hear you and see you perfect.
Thank you. Well, as Matías was telling, I am from a physics department, basically surrounded by physics. So I really enjoy this opportunity to attend these symposiums where we can see the magic of the creation of materials that you carry out. Our work is a little bit more humble. We just try to characterize and assess the functionality of the magic you create, let's say. So I put a bit intentionally here I'm sorry, I would like to change the pointer. Yeah. Intentionally, I put a general porous media in the title of the talk. This will be 95% of porous media and not MOFs. We are a bit new in the area. So my aim here is to present you with a set of tools that are more or less not standard in the community. And basically, I can divide them in three different lines. First is spectroscopy. This is the most common tool of NMR. Maybe you all know them. We already saw some examples of solid-state NMR to characterize materials. If you do solid-state NMRs in solid materials, you're doing basically crystallography. What we're going to do is, we're not going to see the matrix. We're going to set all our pulse sequences, all our approach to only observe fluid inside the matrix. We will try to erase the matrix from our observation data, and we will try to assess the dynamics of the fluids, basically liquids in this talk. In this talk, it will be mostly water, diffusing, absorbing, or doing whatever they do inside the porous media. We use relaxation times how long the lifetime of the information we put into the material inside the porous media will give us information about functionality and structures. And then last of all, diffusion is perhaps the golden standard for measuring transport in porous media. So let's start with an example. This is okay, first of all, we are not using always the standard high field NMR labs. We resort to low fields, and I will show you this very particular instrument that we're using for the MOFs examples. So I start with a very large, let's say, mesopore. This is something that Galo Solelia was doing in UNSAM. They want to characterize the filling with water of titanium oxide nanotubes, and they were pretty sure this had 5 nanometers. However, they were doing nitrogen adsorption, and they had the results show that it was smaller, the pore size. So they were very, very concerned on how these pores were filling. If you have a small pore, it will fill from the walls to the center. If it's smaller, it will make a plug of water and fill toward the ends. And if it's bigger, it will eventually form a plug and grow sideways. So what we do here is pure spectroscopy. These are very, very broad lines. This is static experiments. This is not a magic angle spinning. You see here we had to put it in a logarithmic scale to be able to observe these very small signals. So we have this blue line that comes from the first hydration layer. These 2 peaks is a typical splitting for solid state NMR. So this water is so absorbed in the surface that it behaves for NMR as a solid. Then we have the second layer that has a very small splitting, so the mobility is greater over here. And finally, we have the liquid inside the bulk, this green thing. So we put these systems to different atmospheres, different humidities, and we can very nicely characterize the filling of the mesopores as a function of the humidity we put in the water. And also, if you check the shift of the chemical shift of the mobile signal, you can see that mobility is going faster. It's going towards the 5 ppm that is bulk water. Yes, so as long as you're feeling this center of the pore becomes more and more mobile. So Stefania Gonzalez Solveira had a lot of simulations, and for the 5 nanometers, it looks very, very much like the experimental data we were obtaining. A nicer example from a spectroscopic point of view is maybe mesoporous carbons, and these materials are now, there's a great interest for energy storage, lithium, or for drug delivery, many applications on mesoporous carbons. In particular, Horacio Corti from CONE was synthesizing, and they managed to make something like a bimodal mesoporous carbons with 4 nanometers mesopores and a large amount of micropores below 2 nanometers. So the carbon structure makes a huge mess in the magnetic field. So you have very nice chemical shifts. So water containing micropores will appear very far away from water containing mesopores. So it's very easy to distinguish them. And then you have here bulk water that is present over here. So what we try to do in this work is to monitor the exchange of water between different environments. So we do a frequency correlation experiment. So here in the diagonal, you have this spectra, and this exchange between micropores and bulk water will appear as a cross peak over here. The exchange between mesopores and micropores appears as a cross peak over here, and you have exchange between mesopore and bulk. So this is a very nice cartoon. The reality is a bit worse. So here's the diagonal. As you increase the time you give the molecules to move around the pore system, you start seeing these cross peaks over here, and for a very long time you see all these cross peaks. You integrate and you can have this exchange ratio. So you can see that it's very fast. The red line is very fast between bulk and mesopore. Micropore and bulk is slower, and you have a very complex interaction between micropores and mesopores that give you like a twofold dynamics in there. The second tool we use very much is relaxation. When a molecule comes near the surface, the relaxation times of a molecule will basically be related to the individual movements. Yes, rotations around this axis, let's say. So this is a very fast process, but when a molecule adsorbs in a surface, 2 things may happen. It will walk and then desorb. This residence time will greatly affect the relaxation times because the molecule is static or it's probing the geometry pore, and eventually we'll find relaxation sites. And there is a large variety of things that can happen. You can have hydrogen bond with hydroxides, you can have a catalysis in the surface, you can have electrons for silicium, many amounts of things. There is a model for each one, of course. And basically, you will have a pore relaxivity, we call it. Of course, it depends on the fluid. and you have a structural parameter. So you can know this one and infer the other one, or the other way around, so you can characterize the system. As an example, or if we not consider the surface, then you have that the relaxation times, these two relaxation times that we measured, they are the same. If you confine a smaller pore, then you will shift in this diagonal, but basically the relaxation times are still the same. However, when you put surface interactions, you see a shift from this diagonal, and this is very useful. This is related with activation energy or with absorption energy. You can have a lot of information, especially if you have a catalyzer in your pore system, where the signals appears in these relaxation maps that we call them. You have a very great amount of information over there. So as an example, we had a hierarchical pore system with a gel phase and many big pores. So this relaxation time is related to the surface to volume, the pore size, and you see a distribution of pore sizes over here. If you do this relaxation map, you see the larger pores, smaller pores, and here is the mesh. And this mesh over here, we will look closely. If you change for the synthesis of this polymer the amount of cross-linker, you will be as you have more cross-linker, you will be eliminating these hydroxyl groups over here. So the less cross-linker, the more groups you have, and this surface relaxivity is going high. So you're moving very far away from this diagonal. So you can really characterize the interaction of water with the surface through these hydrogen bonds that are being going on. So finally, and this is mainly the topic of the talk and the conference here, we were working with Omar Azzaroni and Matias and Valdemar also from INIFTA, and they were trying to functionalize CIF8 MOFs, putting a polymer in the surface. And they wanted to see how water was moving through these systems, and well, they had very nice results, and we tried to contribute a little bit for this. So we're going to use here two types of MOFs. A MIL96 that is a very well characterized MOFs, and water can go inside the fundamental cage of the crystalline structure. And this other MOF, CIF8, where water in principle will not go inside the cage, but it will interact with this polymer, and this is our PAVA chains, and they were decorating this with different amount of polymers. So the tool we use, this very strange tool, is called single-sided NMR. It's now the trademark is NMR Mouse for Mobile Universal Surface Explorer. Basically, what you do is you put two magnets opposite, so the magnetic field lines will go out and inside of the magnet. Actually, this is the configuration. And you will have someplace outside of the magnet a very nice region to do NMR ex situ, so you don't have to put the sample in a special container in a 5mm NMR tube or a 4mm rotor for doing solid state NMR. You can put whatever you want over here, and you can do NMR in this region. However, the magnetic field lines are opening very much, so you have a very, very intense gradient. You have to go to a very interesting commercial probe to reach these values. So this will enable to measure diffusion very effectively and very fast. Additionally, you only excite a slice over here from 150 to 100 micrometers. So you can really have a thin slice of your sample detected over there. So basically what you do is you excite in the presence of the magnetic field gradient, and you have this diffusion time where you let the molecules travel through the porous medium. And if you acquire the signal, you will see that you put in this value all the parameters in this B value, and you will basically have a straight line if you have diffusion, pure diffusion, one diffusion coefficient. So this is water contained in porous, mesoporous silica, 3 nanometers, 6 nanometers, 15 nanometers, and bulk water. So you see how a single line describes all the diffusion process. In MOFs, there is something strange. This was already reported some years ago. You have like 2 decays. Here, the MOFs were put also in a water atmosphere, so water went into the system as at will. Let's say it was not full with water. So we have adsorbed water in the border of the crystalline grains and a vapor phase over here. And the rapid exchange between vapor and water gives you this very fast decay function. So there's a molecule in the water phase, it will go to the gas phase, walk very fast, and re-enter the gas phase, the water phase. So you will measure like the diffusion was very, very big. Actually, it goes something like 10 to the minus 7 square meters per second, which is meaningless because water is 10 to the minus 9. So it's very, very fast. However, the water contained inside the cavity, we can characterize very nicely, and this is very consistent with simulated results that were published very recently. And when we see the decorated MOFs, we see the same effect. There is also a very rapid exchange over here, but we see a different diffusion coefficient. It's much faster than the one inside the cage. In principle, water will not go inside the sieve 8, so this water must be in this new porosity, let's call it, or it's absorbing and dissolving in the polymer chains and working all over these regions. So what we did is, using spectroscopy, you see here this very broad line. This is the matrix of the sieve 8, and this is the water absorbed in the polymer matrix. So by inspecting this line, we can characterize the amount of water that is going in. So this is a function, as a function of the amount of polymer put over the crystals. So as the amount increases, the amount of water also increases. You see over here that inside the 96, you still have a lot more water than you will have over here. But the most interesting aspect is not the amount of water, but it's the mobility. So what we see over here is that the mobility of the 96 is somewhere around here. However, almost independent of the amount of content, you have a much higher mobility of the water going through this or mediated through the polymer chains inside this porous matrix. Okay, so this is my 15 minutes. Thank you very much. I hope I was able to show you that there are a wide range of tools, more than spectroscopy, beyond spectroscopy, let's say, that you can use to assess fluid mobility inside porous systems, and we'll hope to continue collaborating with Matias and Valdemar and Omar very soon to have more results in MOFs to show you in the next symposium. Thank you very much.
Thank you, Rodolfo. Gracias, Rodolfo. Muy bueno ahí el resumen. Very interesting, all the range of techniques that we don't use so often as we should. We have other talks in coming events on nuclear magnetic resonance applied to MOFs. Not only for characterization, which is something we have seen many times, but also in order to characterize functional properties such as diffusion of molecules within MOFs and affinities and the effect of polymer cupping on such properties, which is something relatively new. So thank you very much, Rodolfo. Here we have one question from Celeste, which is one of the organizers too, from San Luis. Thank you very much, Rodolfo, for your nice talk. I wonder if it's suitable to apply NMR technique to a system, a MOF system, with a pre-adsorbed molecule in order to determine the main way of interaction with the MOF surface. Can you do that with NMR? So,
yeah, surely. Basically, you can do exactly what I showed here. You can measure diffusion, and if you have the MOF function, you can do several things. You can put different molecules into the MOF and then try to see how the molecules work. When we have to assess a polymer's porous media, we start by saturating the media with alkanes, pentane, heptane. So these apolar molecules, we have a very light interaction with the surface. So then we try to, on one hand, try to obtain structural properties, let's say. And then we start changing the polarity. Water is the most stringent example because it adsorbs very tightly. So you could do this thing. You could use different solvents for your MOF and try to characterize their mobility, or for the particular one you want, you can do diffusion, you can do relaxation measurements and see how strong the interaction is for your MOFs. Yes, you can really apply this.
Excellent, Rolf. There's another question, but maybe one from me in the meantime. let's say I was thinking while you were showing these results with the amount of water absorbed determined by NMR, that it is possible if you create a really controlled atmosphere with a fixed, increasingly higher percentage of water in the atmosphere to measure, let's say, a water absorption isotope from NMR, and in this way, if you can do that, then can you deconvolute maybe two different sites in which water goes in when the pressure, partial pressure is increased?
Yeah, sure. This is exactly what we did here with Gallo.
Right.
Each one of these points is a different isopectic chamber with a different acid, with a different humidity. We left them, I think, more than 3 weeks to stabilize,
Right.
and we just put it in there, and you can, yeah, and then you can do spectroscopy or diffusion, whichever you wish.
Yeah, I was thinking about these absorption, desorption branches in which you, because you don't have another way to do it, to look at the hysteresis loops to, in order to determine whether you have this or not. And yeah, so I see. So it's, let's say, it's too much time consuming for doing it in that way.
No, I think this time we exaggerated, especially being an oxide titanium. Uh, I think this is very, very fast. If you want to do it real time, you want to change the humidity at real time in the experiment. If you want to use the open magnet that we showed, for each measurement, perhaps you should spend minimum half an hour, 15 minutes to accumulate data, because it's an XC2, the signal to noise is very good, but still you need some averaging time. But we could try it, yes.
Okay, perfect. Because it's something I haven't seen, like to characterize in the same way it is characterized by, let's say, spectroscopic ellipsometry and water absorption. Usually you see those experiments, and then you see all these loops, and then you can change, for instance, the absorption, the molecule you want to absorb, let's say alcohols or water or other humidity control media, and then to go and back and forth through these partial pressures to see the loops. Thank you, Rodolfo. Then Alejandro, just to finish, Alejandro también de Córdoba. Fracaroli, thank you for the presentation, Rodolfo. Is it possible to study dynamics of gas phase guests like CO2 or water vapor at different partial pressures?
It is, but the partial pressure should be very, very high, because the sensitivity of NMR is not so great. You see a very small fraction when you put a sample inside a magnetic field. Water has spin 1/2. You will have some of the spins aligned with the magnetic field and some of the spins against. So from 10 to the 23 molecules, you will see something like 0.007% of the molecules will give you a signal. This is the reason that you go to such high magnetic fields. So if there is a lot of gas phase NMR carried out, but you have to increase the pressures. Yes.
Yeah, I know, regarding this, Alejandro asked, I remember that in your group you have studied catalytic behavior of hydrogenation reactions or hydrogen evolution from noble metal catalysts, right?
Yes,
Through
yes. But what we were doing there is preparing hydrogen gas in a para state. We changed it from hot to hydrogen to para hydrogen. But then we did a chemical reaction with a molecule, with a liquid molecule, and we measured the liquid, not the gas.
All right. Okay. Yeah.
To do pure gas, it is possible also, but not in all gases. There's something called
To dilute the phase.
When you transfer energy from a laser to a metal, rubidium, most likely, and then rubidium, if it's in the gas phase, will interact, form a van der Waals molecule with xenon, and then it transfers the electronic polarization. Okay, with the laser, you give energy to the electrons of the rubidium. It makes a van der Waals molecule. The electrons pass the information to the xenon nuclei, and then you have very large signals. So xenon is very much used, and it's a very wonderful molecule because it has 129 electrons. Chemical shifts are really monstrous. So you can see a lot of absorbance and very nice stuff. So this is very much used to characterize characterize gases within porous media, yes.
Then Alejandro is maybe doing some a clarification on the question. He was thinking about level carbon-13 instead of regular, let's say, carbon dioxide. What if you use that isotope?
But also in the gas phase, yes, if you have it, you want to put enriched carbon-13 in a gas phase inside a MOF. This is the question?
I understand that, yes.
Yes, then sure.
Then it's much likely to have some good signals.
Yes.
Good. Yeah, perfect. That's what Alejandro was saying. Bueno, perfecto. Gracias, Rodolfo, por una interesantísima charla y por venir y juntarte con nosotros. Esperemos la próxima hacerlo en vivo. Ya te vamos a notificar, quedas en la lista. Así que bueno, para continuar con la Armada Cordobesa, ya que estaba preguntando Alejandro y estaba preguntando Rodolfo, vamos a pasar